Alright, so this will not exactly solve Project 2, but I'm going to download and work on one of the codes that I already have online to give you some direction here. Okay, so if we go to the Google Drive and you go to our folder and then go to Project 2 and then just take well, first here, check it out. Let's take this one and download it. Okay, save it, open the folder, and we no longer need that. So I'm going to put it in this directory called PROJ2. So if I go into here, open the code, here's where we sit. Okay, if we run through this first time, it should give it. Hang on. Wait. Quit. Now run it. Okay. We get something like this. Now, let me run back and see if it was the one with the spring. Okay, so here is. Okay, here. Wait a minute. I need to do a clear. Okay, now I need to run it. Okay, it should come back and say delta is equal to delta is not defined. On this line 53, it's mad because delta is not defined. So in other words, if I run the code, I can run it to there, to this breakpoint. Delta isn't defined, I do a step and it gives you an error. I'm going to give a different approach towards finding the solution to this one. Here's what we're going to do. First, I'm going to go see if I can find here, get rid of these two, and then go and look at, I just posted this, and let's look at this. Now, I've pre-done this for a second, so it's unfair. Okay, here, let's just close that. Okay, so let's take a look at this. Okay, if you imagine this beam and a undeflected location of, and let's go back and look at this. So we're looking at node 6 in this beam, and we're saying that node 6 is going to have a force placed on it, which is a spring constant of 100 times the deflection. Let's say if it was 1,000, for example. If it was 1,000, how, or even 10,000, but for this case, let's say it's 1,000. So let's look back at this Twitter site. The left is the beam, the right is the spring. So this is node 6 right here. So this right here is node 6 of the beam. Essentially, any point on a beam is going to act like a linear spring if it is linear beam theory, which is all throughout undergraduate education. So therefore, this point, the node 6, actually this is pre-known, I'll show you this in a minute. Node 6 drops 0.85 units. Let me show you that. If I go in and I say delta is equal to 0, and then I run this, what you'll find is, let me slide this up, node 6, okay, there's the deflection. Here, I'll even slide it up. Here's the node, and node 6 drops 0.85 with no force applied to node 6. So, if no force is applied to node 6 was here, and then it dropped right there. Now I've got a spring over here. I've decided just arbitrarily to make it 1,000 because I've made it large enough so that the iteration method we were using will fail. And if you make this 1,000, then I have to put a force on the top of this to push down, and that same force on the bottom of the beam to push up to slip the spring up under node 6, which means that force that I push up on here and this force that I push down on this spring have to be the same. If this spring were sitting under that beam, they're going to be the same. Now what I need to do is, now this is predetermined, but I already figured this out, but I'm going to go figure it out now. I know the spring stiffness of this spring, it was 1,000. It's given. What is the spring stiffness of the beam at node 6? Well, let's go and test that out. I'm going to basically stop here for a moment. I'm going to do a copy and I'm going to do a paste. And I'm going to temporarily put 100 pounds or force units on this. Now what am I saying? I'm shooting to find K1 of the spring stiffness of the beam at node 6. So if I push up with 100 force units, the deflection equals to what? Now, again, the code gave me this, but I'm just writing this down. Let's see what that is. So here, I can go ahead and run this thing again. Okay, so if I step through here, right now, okay, that's not true, but here. Now I'm applying 100 pounds, and let's see what happens. Oh, continue. No. Oh, sorry. Okay. Wait a minute. Alright, so it deflected 1.25, whereas before it deflected 0.85. Now to let you know, alright, so let's go back. So the difference here is 0.4. This is why you see a 0.4 here, meaning that the stiffness of the beam at that point is 250 force units per deflection. Now let's try this. Let's say we did this. Then we ran it. Okay, so what you get now at node 6 is this. 0.85 minus still is 0.4. Now let's try this. Let's try any particular, let's say 200. Run it again. Okay, this time we get a different deflection. But what we've done, and I won't even attempt to do this, but what we've done by doing that is we've changed the force we've applied. So I could subtract these two. I keep getting the 250 is what I'm saying. So if you look at putting a different force on node 6 and looking at the difference in the deflection, that's what you're seeing. You will end up with the spring stiffness of the beam at that node that the spring ends up getting attached to. Now imagine that you're doing this. Now that I know what this stiffness is, I did a little experiment using the finite elements to get this term right here. Now what I have to do, I have to put a different force here. Not 100, but something else. What do I need to push this one up and push this one down so that they're perfectly lined up and I could just slip the spring right up under the beam and let loose? Well, whatever it is, the force has to be the same on both. And the deflection has to be, now, hang on a minute. That's supposed to be 250 right here. So imagine that this is 250. Okay, so we got a problem. It's 250 delta 1 is going to end up 1,000 times delta 2, which means you slide this under and you'll get, oops, sorry. So if I take this 250 delta 1, error right there, equals to 1,000 delta 2, I get delta 1 is equal to 4 times delta 2. But also, I have to realize that if I'm going to move this one up and this one down, the delta 1 plus delta 2 has to be 0.85, which was the free deflection of this beam. Okay, so that means delta 1 plus delta 2 is equal to 0.85. I can take that equation and slip down here, take this one and put together, coming up with delta 2 is equal to 0.17, so the force is equal to 170. Now let's check this out. Is that the case? Let's see, 170. So I'm just putting in 170. I'm not doing anything else. So I put in 170 and I get this value out of it. Now the question is that correct? Well, the key is, now that I have delta, I should have a delta value. What is my delta value? .17. Well, now that I put in the 170, let me just go ahead and cut this out and comment it, and let's see what happens here. If I go back in with the new delta, what is the force that got applied? Delta was 0.17. Lo and behold, it's 170. So I can keep doing this one over and over and over. And I essentially iterated twice, so to speak. I used the code to find the first deflection. And I took that deflection and used this simple logic, with the exception of the fact that I wrote down 200 where it should have been 250 right here. Because that's the 250, that's the spring stiffness. So be aware of that. Wait a minute, I don't know what's going on here. So this 250 should be written right there. And that's essentially a two-pass evaluation of how to implement this. Okay, I hope that helps with the spring part of Project 2. That's a simple, logical approach towards this. It can be quantified differently, but for right now, I think that's good.